Now I'm going to talk about something called multidimensional scaling, which is basically a class of methods with similar goals. Some of them are linear like PCA, some of them are not. But the idea here is that we want to find low dimensional representations of high dimensional data such that the distances between the points match as well as possible the dissimilarities between the original points. So basically what we want is, okay, we want to have this low dimensional representation, and it's okay if we lose some of the information from the original space, as long as if we take two different points in the low dimensional representation, their distances are equivalent to their distances that they had in the original data set. Of course, absolutely speaking, it cannot be, because the more features you have, the larger the value of the distances. So the number, let's say the value itself of the distance will not be the same, but taken as a whole, if you take the data set as a whole, and you take two data points and they're close together, that should mean that they were originally close together in the original data space. And if, again, you take the new data set with the new features and 2 points are very far away from each other, then you can infer that they were also far away from each other in the original data set, okay? And the final space is usually Euclidean. So it's like, again, a scatter plot of 2 or 3 dimensions, or 4 or 5, doesn't matter, as long as it's still Euclidean. But there is usually no special restriction as to where the original dissimilarities come from. So you may have points coming from a graph, for example, where you define the dissimilarities between the points explicitly, and so on and so forth. We're not going to discuss that too much, but all you have to know is that the original dissimilarities could come from actual measurements of the similarities, if that's something that you have measured, for example. Yeah, and in this case, it's interesting to see that MDS is more or less the same as we had before, but the input now is an n by n distance matrix. So it's not a feature matrix anymore as it was with PCA. PCA had to work with the features, but MDS actually works on a distance matrix where each cell of the matrix is a pairwise distance between 2 data points. So if I take like row 10, column 5, that is the distance between the 10th data point and the 5th data point. And then you compute this for all possible pairs of points from your data set. So actually it ends up being like a triangular matrix instead of a square matrix, but usually it's a square matrix. It's a triangular matrix that is, symmetric over diagonal, because the distance between the 10th and the 5th point is the same as the distance between the 5th and the 10th point. Usually. It might not be, but usually it is. And the final result still has n rows, because it's still n data points, with some lower dimensional here, as whatever you want. So as you can see, the initial dimensionality doesn't matter here. Could be 100, could be 1,000, doesn't matter, as long as you can compute distances between pairs of points. Okay, and this distance could be Euclidean, could be whatever else you would want it to be. And this is interesting. This is an interesting example. I'm just gonna, yeah. It's a data set where there is a correlations between crime rates in the United States. So you can see here that there's these places with different measurements for each crime. So I don't know what is 1, 2, 3, 4, 5, 6, 7, but it's yeah, there's states, right? So for example, you can see that I don't know which ones, but there are states. You can see, for example, that larceny and auto theft in this. Let me go back here because I'm getting confused now. So yeah, so for example, you can see that these guys here, they're close together because they have a good correlation, for example, between assault and murder and assault and rape. They are, let's say, they have a good correlation here, 0.81, 0.70, and 0.80, for example, between these two guys here. Sorry, guys. Let me start again. I confused this one with the previous one that I was talking about. This is correlation between crime rates. So it's the data points here are the crime rates themselves. They're not the U.S. states. I'm sorry. Let's start again with this thing. We have 7 types of crimes here. So murder, rape, robbery, blah, 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 blah. And they computed how correlated the crimes themselves are. So like how when murder happens, assault also happens. Or when rape happens, assault also happens. Sorry, I got completely confused with the previous example. So for example, they measured this and they found out that there is a very high correlation between 4 and 1, which is basically assault and murder. And there's also a lot of a very strong correlation between assault and rape, which is number 2. And that's why if you look at the graph here, you can see rape, assault, and murder. They're kind of like they're close to each other more or less here because they are highly correlated. And also like larceny and burglary, for example, larceny and burglary are basically 5 and 6. So 5 and 6 here. So 0.80. That's also a very large correlation, right? 0.80. So whenever there's larceny, there's usually burglary. They're very correlated. And then you see that in the map that murder, assault are close to each other, rape and assault are close to each other, larceny and burglary are also close to each other, which is what you expect to see in an MDS map. And is that if the original values were very correlated, highly correlated, or just highly related in whatever distance you decided to measure, in this case it's correlation, could be Euclidean, they should be close together in the map. On the other hand, for example, if you take larceny with 6 and 1, which is larceny against murder, then you can see that they're very far away. So murder is over here, larceny is over here. So when you look at larceny and murder, they're very far away from each other, and you can say, wow, okay, so there is not a large correlation between larceny and murder. And the same thing with auto theft. So if there's no specific correlation between murder, well, there's very little specific correlation between murder and auto theft, so 0.11. And again, you can also see this in the graph, in this representation. You can see auto theft is over here, murder is over here, so they're very far away from each other. And this fits with the thing that I was talking about before. If 2 things are very close, then you can infer that they have low, like they're very similar somehow in the original data set. And if 2 things are very far away from each other, then you can infer again that they are also far away in the original data set. And then there's, for example, rape and murder here, which is 52, which is somewhere in between. And again, you can see that it's like somewhere in between here. It's not too close, not too far away. It's just somewhere in between, so. And you can find these for all other kinds of things, like, for example, rape and robbery. Rape and robbery, for example, 55, and then you can see rape and robbery here. It's like, yeah, they're not close, but they're also not very far away, and so on. So this is I think is an interesting example to see how such a graph like this can be a good representation of the matrix itself as a whole. As a visualization, you look at this thing and then you can infer things from your original correlation matrix, okay? Sorry for the confusion in the beginning. This is the general procedure for obtaining an MDS projection. It's a little bit different than PCA, and there are some analytical solutions using linear algebra, but in general, we use gradient descent for this. So we'd start with an initial configuration. Could be random, could be a PCA, could be whatever. You just start with an initial random configuration of points in the low dimensional representation that you're looking for. In this case, for example, we had a 2D representation, so we would start with some random points into 2D plane, or some other form of initial configuration. Doesn't matter. This is just the initial guess of the gradient descent. Then you evaluate a certain cost function, and every MDS has a cost function. For example, in this case that we were analyzing, the cost function is that we want to minimize the error between the distances in the low dimensional space and the distances in the high dimensional space. I'm going to talk about this in a second, but just remember that there's a cost function that determines how bad is this new low dimensional representation. Then if the cost is low enough, let's say, or if the maximum number of iterations was reached, then you stop, right? Because it's gradient descent, and sometimes you have, at some point you have to stop. So you can either stop because you've done a certain maximum number of iterations, or you can stop because you've reached a certain threshold of cost that's low enough that you're willing to accept it. If not, then you move each point. So each of these points that you put in this initial guess, you move it slightly towards the direction where the cost function is minimized, right? So there is a certain direction for these points to move where the cost function will be minimized, and each of them has its own direction to move for, because you started with a random thing. So every point needs to move towards its optional position, right? So if you haven't reached the point where you want to stop, you have to move the points a little bit, and then you move them slightly according to the learning rate. So each of these points has a direction to move towards where you get the highest cost reduction. And then you keep doing this and doing this and doing this until, again, you do it a certain number of times, or you find that the cost is low enough that you can stop. Yeah, go to 3 because you're doing this all over again. And this is just again, a toy examples, right? A toy example of how these things work. You can consider the colors here as being like the original features. So I want to have similar colors close together, right? I started with a random initial configuration in 2D. So you have these points and they have colors, but they're completely random right now. That doesn't matter. That doesn't mean anything. And then what happens is, okay, I decided that I don't want to stop. I still want to go. So I find the gradient, for example, for point number 1, and then I move it a specific amount of the distance depending on the learning rate. So it comes to this point. Then I do the same for point number 2. I found out that the direction here for point number 2 is like this direction because I want to get closer to 4. And then I move it a little bit because of the learning rate. And also remember that every step there are both attractive and repulsive forces acting on each point, because not only I want to get closer to 4, but I also want to get far away from the other stuff that's not like me, right? And for example, in this case, I moved 3 this way because I found out that this was the gradient for 3. And the reason why I'm not moving directly, you might think, well, why are you not moving directly towards 7? Since 7 is also red. It's because, again, I want to move towards red, but I also want to move away from the green guys. So I cannot just get inside the green guys and forget about them. I actually have to consider that I want to get closer to 7, but I also want to get far away from green, right? So all these forces are acting at the same time. That's why it's not just a matter of, bling, that's it, you have a perfect solution. There's so many forces interacting at the same time that this optimization process is actually quite complex. And so on. So you keep moving these points around, then you recompute the cost function, and then you decide that you want to do it again. You move the points around a little bit more until you get to a solution at the end. And then you say, okay, well, this is the solution. It's not perfect. It's never perfect, but it's something that you can use to reason about. And these are examples of cost functions. Like I said, there's always a cost function, but different cost functions represent different goals. So back in the beginning, I said, there's never a silver bullet. There's never one projection that fits all the possible, that fulfills all the possible goals and is a final solution. So each of the cost functions that you could have that you optimize in this process, they represent different things. So these are all very old stuff because the MDS is also something that's been around forever. But this cost function, for example, from Kruskal, this is basically just what we've been discussing. It's minimize all pairwise distances as much as possible. So the final solution should be as accurate as possible regarding all pairwise distances between all points. And then there's Salmon stress came like 5 years later to deal with a little bit of a problem, which was, you know, Salmon realized that you cannot have a good representation of the data if you are trying to optimize for all pairwise distances, disregarding everything. And the reason is because, you know, it's just the high dimension space is just so complex that you can never have a good representation if you never throw anything away, or if you never reduce the weight of some things to favor other things. So you should have a way to reduce some weights between some pairwise distances in order to favor other which are more important. And in his sense, what he wanted was, you know, I want to minimize the pairwise distances, but the larger is the original distance. So this is the original distance over here that we're dividing. The larger is this thing, the less I want this to matter. So so if 2 points are very, very far away from each other in the original space, which is what is represented by this value over here, I actually don't care about that too much. So I divide by this thing so that the cost actually does not go up too much, because I'm dividing by a large value here. So that specific component of the cost is not very, very important. It's just a little bit. And by doing this, Salmon realized that the final results actually were more interesting, because it was more like about looking for points that are close together and then optimize them. And the points that are far away from that don't matter too much. So you shouldn't really look too much about on points that are far away. You should only look for like clusters of points, for example. This slide over here is that which I was explaining. It's very important because there are some mathematical definitions here that you're going to need in order to do the assignment, right? I guess you've already taken a look at the assignment itself. You have to implement Salmon mapping. And this is where the formula is for implementing that. And of course, if you think this is confusing, you can go to the original paper and look at that instead. I think the only major difference between the way that I wrote it here and the way that he writes it in the original paper is that he separated the 2 dimensions of y. So he gives the partial derivatives for the first y, like the first at the x-axis, let's say, of the 2-dimensional representation, and the y-axis, and it makes it separate. And I compress them together. That's why I put here like vectorized, because actually these will give you, mathematically speaking, they're not correct, but they're correct if you consider it as like numpy vectorizations. So so this will give you the partial derivatives for both axes at the same time, which is not how he does it in his paper. He gives it separately for each of the 2 ones. And I thought it was, you don't have to, because, you know, they're the same. It's just that they're done separately, let's say. So take it as being like vectorized numpy operations here. And then it works. So this is where the partial derivatives are that you have to use to do the optimization. Well, you may have thought that you would never need any of this, but you were wrong, because you have to do it for assignment 4. So good luck with that. Come back to me with questions later if you need help with this, but I hope it's more or less clear from the slides and from the original paper. Yeah, you wish, David, you wish. So I wish, I want to show you a small comparison now between these algorithms that I've discussed so far, which I think it's quite interesting to see. And again, I'm using this I'm using this as a visualization thing. So I'm using dimensionality reduction here as a visualization tool, and then I'm going to compare them so you can have a more clear understanding of the differences between them. Deepak is asking me, can you please explain the variables in the Semel mapping formula? Yeah, I can go over them in general, overall. So let me see if I should go back over here. Yeah, so this is the cost function, right? Dij is the distance between points I and j in the low dimensional representation. So for example, if you're using Semel mapping to map something from a high dimension to a low dimensional, then d is the low dimensional distances between I and j. And sigma, or delta, sorry, delta ij is the distances between ij in the original space. So every pair of points has distances in the original space. For example, you just take the original vectors and calculate the Euclidean distance. And they also have distances in the final low dimensional representation, which is again just for example, just an Euclidean distance in the final 2 or 3D representation that you found. So the cost here is basically take the low dimensional representation minus the low dimensional distance minus the high dimensional distance. This is the error, right? Because you want this distance to be low. That's the goal of the optimization. You want the difference between these distances to be low. Then you square it, because it's you know, like when you do with a linear regression or most other costs, you have this squared error, because then it becomes positive, and then you want to penalize outliers and so on. So you square it, becomes positive. Then you divide by the original distance in the input space, so that the larger is this thing over here, the smallest this component actually matters. Then you sum all of it for all pairs of points. So you have the sum of squared errors. It is literally the sum of squared errors, but divided by this kind of a, let's say, factor here for penalizing larger distances. And then at the end, you just normalize it by the sum of all the original distances here. Actually, this is just a constant, so it doesn't really matter too much. But it's a way to scale down the error in a way that makes sense for the optimization. But that's a constant. And then the gradient descent basically is like this. Again, as I said before, you start with a random thing. So for example, if it's 2D that you want to have, then you just start with a random 2D thing. So if you have 1,000 data points, you start with 1,000 random 2D points that were in a plane or something. It's random, doesn't matter. Then you have it. It's your initial step. That's T0, let's say. Then the new T here, the Y, so for each point, again, you remember that we discussed at every step, each point will move a little bit towards the direction that reduces the cost the most. So then how do you do that? Well, the near representation of your point is equal for every point, okay, is equal to the previous one. So the one that you already have, which is random initially, minus a certain alpha here, which is the learning rate. Let's say you assume it to be 0.3. In the original paper, it's 0.3. Then it's in the original paper. Maybe you can play with that a little bit. So minus the original, sorry, the learning rate times a certain delta here, T, which is the gradient, right? So, or first the previous point minus learning rate times the gradient, which is exactly what we saw in the little animation that says the initial point moves towards the gradient a certain amount of learning rate. So then the question is, of course, what is the gradient, right? What is the direction that this point has to move towards? Well, that is the partial derivative of the cost regarding this specific point divided by the second partial derivative of this point of the cost regarding this specific point. So it's basically first derivative divided by the second derivative. And then, of course, I say, yeah, well, what are the partial derivatives? I'm not going to come up with them myself, right? Of course not. So the first partial derivative is minus 2 divided by c, which is just a constant. Again, it's just the sum of all the original similarities. It's a constant. You can pre-compute this. And then times original distances minus low dimensional distances divided by, and so on. And then you just replace them with the stuff that you already know what it is: original distances, final distances, and so on. And this is yi minus yj. And the reason why I say it's vectorized, it's because yi is a vector and yj is also a vector, right? Because y here is the low dimensional representation, and your low dimensional representation is like 2D or 3D, for example, and that's a vector. It's a vector with 2 elements. So when I say yi minus yj here, I mean a vector, the vectorized subtraction between these two things. And then you do that, you get a vector here, and then well, I'm going to leave it there to scare you. So and then you have this, and then you do it times whatever you get from this computations here. I say it's vectorized because it's literally vectorized. You do this, and then you do that times the result of this, and then you have it. And then you sum for all the j that's different than I. So you don't sum this for when you have the same. So you don't compute distances between I and I, like 1 and 1. The distance is always 0, right? So you don't do that. If you do that, actually you end up with division by 0 here. So which is obviously not possible. And it's exactly the same thing for the second derivative. You just keep applying the stuff that you know. Delta here is the original distance. D is the low dimensional distance. And again, I say this is vectorized because yi and yj are vectors and not numbers. It's different than delta and d, because delta ij is a number and d ij is a number, while yi and yj are actually vectors. So, and actually this square thing here is vectorized. And again, why do I say this is vectorized? Because you cannot square, if you ask me like, how do I square a vector, right? What does that mean? Should I do a dot product of the vector with itself? No, it's a vectorized square, and that's why I'm saying it's vectorized. So it's, for example, if you have 2 dimensions, then yi minus yj squared is basically yi minus yj element wise, and then square element wise again. So it becomes a vector. Because if I didn't do like this, I would have to basically clone the derivatives 2 times for each dimension, which is kind of weird, just to make sure that there are no vectors in this thing. And I think you can understand that this is vectorized. So it's just element wise vectorized operation here. Okay. You should implement this from scratch. You can find it. So I have 2 questions. Here's one from David saying, should we implement this from scratch? Yes, you should implement this from scratch. That is the assignment, okay? Using NumPy. You do find this, you don't find this in, actually, you do find this in scikit-learn, I think, if you use a specific cost, if you define a specific cost function, but you should not. You should implement this from scratch. And what is the necessity to work on the second derivative? That comes from the original paper. If you need to look into that, you will understand, but it's part of how the optimization is defined by the author. It's a good question. I'm not sure exactly why you cannot do without that. But he does a theoretical analysis of the convergence of this, which I unfortunately cannot do here because I don't remember exactly the steps of the proof. But the original author discusses exactly why this thing converges better than not using this. So please look at the original paper for that. Yeah, but yeah, implement this from scratch using NumPy. And good luck making it efficient.